Hello and welcome to Engineers Mindset. So this is the second video on electric force and Coulomb's law. In the first video, we did an introduction and we solved an example in that video to back up our introduction. I will leave the link of that video in the description of this video, so you can do well to click the description to watch the video for proper understanding. Now, in this video, we are going to consider this question to explain the concept that we learned in that video. Now, this question simply says that 2-point charges are held as shown below. If Q equals 1 microcoulombs, find the resultant force in the A plus 4Q charge and B minus Q charge. Okay, so as said in the previous video, we are going to be employing vectors in solving this problem. Now, to employ our vectors in solving this problem, there is something I want you to keep in mind. Let's consider a Cartesian coordinate system. We have this and we have this. Now, when charges move vertically upwards, we call this plus J axis. And if charges move vertically downwards to locate any charge, we call this negative J axis. But if charge moves to your right or towards the right, we call this positive I axis. But if the charge moves to your left, then you call this negative I axis. Now, you have to keep all of this in mind when we start solving, because we are going to be playing around with this in that question. Now, another thing I want you to do is, we have been given the coordinates or the arrangement of these charges as this. This is plus 3Q charge, and this is plus 4Q charge. This is negative Q charge. So let's call the plus 3Q charge Q1. Let's call this charge Q1. Let's call this charge Q2. Okay, let's use capital letter just to separate them. Let's call this charge Q1. Call the plus 4Q charge Q2. Call the negative Q charge as charge Q3. Now, in the first question, you're asked to find the resultant force in the plus 4Q charge, which means the plus 4Q charge has been made my reference point or reference charge. So if we're looking for the resultant force acting on the plus 4Q charge, that means this plus 4Q charge, which we just called Q2 now, which means Q2 now becomes my reference charge. So reference charge is now going to be what? Q2. So what this means is that we move from the reference charge to locate every other charges. Okay, you move from the reference charge to locate every other charges. So we call the reference charge Q2. Okay, now we want to find first the force of attraction between the plus 4Q charge. So that simply means the force of attraction between plus 4Q charge and plus 3Q charge, and that between plus 4Q charge and the negative Q charge. And we call negative Q charge Q3, and we call the plus 3Q charge Q1. Okay, so this means now that the force of attraction between charge 1 and 2 is now going to be K Q1 Q2 all over. Remember, in vectors form, I said this becomes magnitude of charge 1 and charge 2 all squared, okay, times their unit vectors. And unit vector simply means the position vector R12, okay, divided by magnitude R12 magnitude. Okay, so let's find. Now we know our charge 1, which is plus 3Q. We know our charge 2, which is plus 4Q. Now we're looking for the force of attraction between these two charges. Of course, this is going to be a repelling force because the two of them are positively charged forces, so they cannot attract, rather they will repel. We want to find the force between them. Okay, now I said that the plus 4Q charge in this case becomes our reference charge. So this means you have to move from the reference charge to locate charge Q1. That's how you go about it. Since this is my reference charge, or Q2 in this case now, we have to now move from Q2 to locate Q1, because Q1 is plus 3Q charge. So we are considering the force of attraction between the plus 4Q charge and Q1. That's the first thing we are doing. Then after that, we look for the force of attraction between plus 4q charge and negative q, which invariably is the q2 charge and q3. So this means now that q2 is my reference charge, and as such, I will move from my reference charge to locate the other point. So the position vector between charge 1 and 2, R1, 2, is simply going to be equal to move from the reference charge and locate charge Q1. So if I move from the reference charge, observe that I am moving upwards and I have covered a distance of 3 meters. And remember, I said if you're moving upwards, the vector notation for that is positive j. That means the position vector between charge 1 and 2 is simply 3j, and it is positive. Okay, having found this, the next thing is to find the magnitude of the position vector. Magnitude of charge 1 and 2. Magnitude simply means taking the square and square root of that given position. So 3 all squared. So the square root of the position all squared. Now this simply means that the magnitude R1 to 2 also remains the same, which is equal to 3. Now having found the position vector and the magnitude, let's now plug that into this equation. Therefore, the force between charge 1 and 2 is taken simply as, remember what K stands for? K is 9 by 10 to the power of 9 multiplied by Q1, and Q1 happens to be the plus 3Q charge. So multiply by 3Q charge times Q2. Q2 happens to be my reference charge, which is plus 4Q. So multiply by plus 4Q all over the magnitude of the position vector. And the magnitude here give us 3. So you have 3, not forgetting all squared. So simply 3 squared. Multiply this by what? Unit vector. Position vector divided by the magnitude. And position vector is 3j. So you have 3j all over the magnitude itself give us 3 all over 3. So this simply implies that the force of attraction between charge 1 and 2 is now going to be less, okay, it's now going to be, this is 9 by 10 to the power of 9 multiplied by 3 multiplied by, remember earlier in the question, it was given that Q is taken as 1 microcoulombs. So in place of Q, we have times 1 by 10 to the power of negative 6, because 1 microcoulomb simply means 1 by 10 to the power of negative 6. Okay, so multiply by, we have 4q here, that becomes 4 by 1 by 10 to the power of negative 6. Okay, the whole of this divides by, now 3 squared over here gives us 9. This multiplied by the unit vector. So 3 divided by 3 is 1. I am left simply with j for the unit vector. So multiply by j and you have this. Okay, so let's evaluate everything at the numerator and see what we are going to obtain. You can do that here. So I'm going to be pointing everything at the numerator. Do well to point along with me. In case there's any calculative error, you can also do well to point it out in the comment section. Thank you. So everything at the numerator gives me 0.108. Not forgetting we have j there. So multiply by j divided by denominator is 9. So now we find 0.108 divided by 9. This implies that the force of attraction between charge 1 and charge 2 is going to be equal to, this gives us 0.012 in the j directions in newtons. So this is the force of attraction between the plus 4q charge and the plus 3q charge. Okay, now having done with this, that is not the end. We are asked to find the resultant force acting on the plus 4q charge. So we still need to find the force of attraction between the plus 4q charge and the minus q charge. In this case now, between Q2 and Q3. Okay, so next we find F2 to 3. So this is going to be equal to once more K multiplies Q2 multiplies Q2 multiplies Q3 all over the magnitude of the position vector between charge 2 and charge 3 all squared multiplied by the unit vectors which indicates the position vector between charge 2 and 3 all over the magnitude of the position vector between charge 2 and charge 3. You have this. Okay, so let's start by calculating our position vector. So R23, position vector between charge 2 and 3, like I said, since charge 2 is now my reference charge, you always move from your reference charge to locate the other charge. So you watch now, you're moving from charge 2 and you're moving towards your right. So remember the vector coordinate I drew earlier. If you're moving towards the right, we say this is simply going to be taken as what? Plus I. So from the reference vector, you're moving to your right, which means it is positive. And distance covered in this case is 4 in the I direction. So that means arrow 2, 3 becomes 4 in the I direction. Now, having found this, the next thing to do is simply find the magnitude of this position vector. So magnitude, the magnitude of charge 2 and 3 simply becomes the square root of the square of the distance apart. So we have square root of 4 squared, which also implies that R23 magnitude remains 4 meters. Now, having found this, we can now plug into this equation. Therefore, the force of attraction between charge 2 and charge 3 is now going to be equal to, we said K remains 9 by 10 to the power of 9 multiplies Q2, and Q2 is my reference charge, which is the plus 4Q charge. So multiply by plus 4Q, okay, multiply by Q3. Q3 is now the new charge, which is minus Q. So multiply by negative Q all over the magnitude squared, and magnitude gave us here as 4. So you have 4 squared. Now multiply by the unit vector, which is position vector divides magnitude, and position vector we obtain here as 4i. So multiply 4i divide by 4, which is the magnitude. Okay, so we can continue here. So this simply implies that the force of attraction between charge 2 and charge 3 is now going to be equal to, so remember, 9 by 10 to the power of 9 multiplies. Now we have 4Q, and remember from the question, Q was given as 1 microcoulombs. So 4Q becomes 4 times 1 by 10 to the power of negative 6, because 1 microcoulomb is 1 by 10 to the power of negative 6. Okay, multiply by minus Q. Once more, Q was given simply as 1 microcoulomb. So minus Q becomes minus 1 by 10 to the power of negative 6 all over magnitude squared. So 4 squared here gives us 16. Not forgetting the unit vectors, 4 divided by 4 is off, so we are left with simply I there. So multiply here by I. So this simply implies that the force of attraction between charge 2 and 3 is now going to be equal to, so as usual, I will multiply the numerator entirely. So do well to multiply along with me, and if you spot any calculation error, do well to keep it in the comment section. All right. So everything at the numerator gives us 0.036. Not forgetting there's a negative sign here. So we have negative 0.036, and then we'll have the I direction. So multiply by I all over 16. Now let's divide these two and see. This simply implies that the force of attraction between charge 2 and charge 3 is now going to be equal to negative 0.036 divided 16. So this simply gives us negative 2.25 by 10 to the power of negative 3 in the I direction. So this is the force of attraction between charge 2 and charge 3. But from the question it says find the resultant force. So we have to look for the resultant force between these 2 point charges. Okay. Therefore, resultant force FR simply means summing of the two forces obtained so far. So we have the sum of the force in charge 1 to 2 plus the force between charge 2 to 3. So this is going to now be equal to, we obtain F1 to 2 over here as 0.012 in the J direction. So we have 0.012J, and we obtain force between charge 2 to 3 over here as negative 2.25. So minus 2.25 by 10 to the power of negative 3 in the I direction. So this becomes the value of the resultant force between those point charges. Now, the B part of the question says also find the resultant force in the negative Q charge. So what this simply means now is that we are now going to make the negative Q charge our reference charge. And once you pick out your reference charge, you move from your reference charge to locate all the other charges. So let's start the second part of the question. All right, welcome back. So let's delve into the second part of the question. The second part says we should find the resultant force in the negative Q charge. So this simply means now, remember we call the negative Q charge our Q3. So Q3 now becomes my reference charge. So the reference charge is now going to be Q3. Now let's find the force of attraction between Q3 and Q2. Okay, so F2, okay, it becomes F3 to 2 because 3 is now the reference charge, so 3 comes first. Now this is equal to, remember, K Q3 Q2 all over the magnitude between charge 3 and charge 2 all squared multiplied by the unit vector, which is the position vector between charge 3 and charge 2, divided by the magnitude of the position vector between charge 2 and charge 3. So let's find the position vector R3 2. Not forgetting the direction, if you move from the reference point to the right to locate a charge, it is positive I, but if you move to the left to locate a charge, it is negative I. Keeping that in mind. Now, Q3 is my reference charge. I will move from the reference charge to locate charge Q2. Observe that I am moving backwards. Total distance covered is 4 meters, but I am moving backwards in the I direction. So that becomes negative I. So distance between charge 3 to 2 automatically becomes minus 4 in the I direction. Having found this, the next thing you do is simply find the magnitude of that distance, R3 to magnitude. This simply means the square root of the square of the given position. So you have negative 4 all squared. Now this is going to be equal to the square root of negative 4 squared gives you 16, which implies that the magnitude of the position vector between charge 2 and charge 3 is simply going to still be what? 4, and you have this. So you plug this now into the formula. So from the formula, F3 2 is now going to be, remember K, and K is 9 by 10 to the power of 9 multiplied by Q3, and Q3 is a negative Q charge, which is minus Q multiplied by Q2, and Q2 remains the plus 4Q charge. So multiply by plus 4Q all over magnitude squared. And magnitude gave us as 4. So you have 4 all squared multiplied by unit vectors, which is position vector. And position vector here is negative 4I divided by the magnitude. And magnitude is simply 4. So divide by 4. So the force of attraction between charge 3 to 2 is now going to be equal to, this is 9 by 10 to the power of 9 multiplied by, we have negative Q, but from the question, Q was given to us as 1 microcoulombs, and 1 microcoulombs is simply, remember, put down your negative sign, so we have minus 1 by 10 to the power of negative 6 multiplied by plus 4Q, that's 4 times, again, Q remains 1 by 10 to the power of negative 6. Okay, all over 4 squared here gives us 16. Multiply now by, remember, negative 4 divides 4, this gives us negative I. So the 4 cancels out. Alright, so as usual, I'm going to be pointing everything at the numerator. Do well to point along with me. Should in case there is any calculation error, don't also fail to point it out in the comment section. Alright, so the force between charge 3 and 2 is now going to be equal to, so observe that if we multiply everything at the numerator, this negative sign and this negative sign multiplies and becomes positive. All right, so let's obtain the value and see. So everything at the numerator gives us 0.036, not forgetting the I there, so multiply by I all over 16. So this simply implies that the force of attraction between charge 3 to 2 is going to now be equal to, divide that by 16. We have simply 2.25 by 10 to the power of negative 3 in the I direction. So this is the force of attraction between charge 2 and charge 3. So you observe that this force of attraction is actually positive compared to the first force of attraction where we saw between charge 2 to charge 3 that gave us negative. Okay, but it doesn't end there. We also need to find the force of attraction between the negative Q charge and the plus 3Q charge. We'll find now between the negative Q and the plus 4Q. Now let's find between negative Q and the plus 3Q charge. So once more, my Q3 or my negative Q becomes my reference charge. So I have to now move from here to locate here the plus 3Q charge, which in this case is Q1. Okay, so the force of attraction, force between the charge 3 to charge 1. So force between charge 3 to charge 1, this is going to be equal to, remember, K Q3 Q1 divides by R31 all squared. Remember, multiply by unit vector, which is the position between charge 3 and charge 1, divides by the magnitude of that position between charge 3 and charge 1. So you have this. So let's find the position vector between charge 3, R3, and charge 1. So R31 becomes, so you simply move from charge 3, which is your reference charge, to locate charge 1. So remember once again, if you're moving from the reference charge and you're moving upwards, is taken simply as positive J. But if you're moving downwards, it is taken as negative J. If you're moving to the right, it's positive I. To the left is negative I. So let's do this and see. I want to locate charge Q1. First of all, I move from here, the reference charge, to charge Q2, covering 4 meters, but that is not where charge Q1 is. Now, remember, this 4 meters is moving backwards negatively. So, first of all, I covered negative 4 in the I direction, but I am not yet at charge Q1. So, I still have to move from charge Q2 here upward. So, I am moving vertically upwards to locate charge plus 3Q. And I cover the total distance of what, 3 meters, moving vertically upwards, which is what, the plus J direction. So which means my position vector now becomes what, moving here backwards minus 4I, moving upwards plus 3J. Therefore the position vector becomes minus 4I plus 3J, and you have this. Now we need to find the magnitude of the position vector. So magnitude of the position vector between charge 3 and 1 simply becomes, you take the square root of the sum of the square of the individual terms. So you have minus 4 all squared plus 3 all squared. Now this is equal to square root minus 4 squared becomes 16 plus 3 squared becomes 9. So magnitude of charge 321 is now equal to the square root of 16 plus 9 gives us 25. This simply implies that the magnitude of the position vector between charge 3 and 1 is simply going to be the square root of 25, which equals 5. So this is the magnitude of the position vector between charge 3 and charge 1. Having found this, then you recall, now, having found this, then you simply plug everything into the equation. Therefore, the force of attraction between charge 3 and charge 1 is going to now be equal to, so we said K, and K has a value of 9 by 10 to the power of 9 multiplies by Q3, and Q3 happens to be negative Q, so you have times negative Q multiplied by Q1, and Q1 happens to be plus 3Q, so multiply simply by plus 3Q all over the magnitude of the position vector all squared, and we obtain the magnitude of our position vector to be 5, so you have all over 5 squared. Multiply this by unit vector, and unit vector is simply position vector divided by the magnitude. Now the position vector is this, so you have minus 4i plus 3j all over magnitude is 5, all over magnitude, and magnitude gave us 5 over here. Okay, so you see now that the force of attraction between charge 3 and charge 1 is now going to be equal to, not forgetting from the question, Q was given to us as 1 microcoulombs. Therefore, you have 9 by 10 to the power of 9 multiplies, this is negative Q, and Q is 1 microcoulomb. So that becomes negative 1 by 10 to the power of negative 6 multiplied by plus 3Q, and 3Q, Q again is 1 microcoulomb. So you have multiplied by 3 multiplied by 1 by 10 to the power of negative 6 all over 5 squared here gives us 25. Now this multiplied by, keep in mind, negative 4i plus 3j simply means negative 4i divides by 5 plus 3j divides by 5, and you have this. So as usual, I will simply multiply all through the numerator. So do well to multiply along with me to avoid any calculation error. And in case you spot any calculation error, do well to post in the comment section. Okay, so the force of attraction between charge 3 and 1 is now going to be equal to, let's multiply the numerators through. So everything at the numerator gives us negative 0.027. Not forgetting there's a negative sign here, so that's how I have negative 0.027 divided by 25. Now for the unit vectors, let's find negative 4 divided by 5. That gives us negative 0.8 in the I direction, plus let's find 3 divided by 5. That gives us 0.6 in the J direction. Now at this point, I will simply find the ratio 0.027 divides 25. Therefore, force between charge 3 and 1 is equal to negative 0.027 divides 25. This gives us negative 1.08 by 10 to the power of negative 3 multiplied by negative 0.8 in the I direction plus 0.6 in the J direction. So all we need to do now is expand this bracket using negative 1.08 exponential minus 3. So this simply implies that the force of attraction between charge 3 and 1 becomes now, so let's multiply negative 1.08 by 10 to the power of negative 3 by negative 0.8. So observe that negative signs cancels out here and we have a positive value. Okay, so that gives us 8.64 by 10 to the power of negative 4 in the I direction. Okay, now negative times plus becomes negative. So let's obtain 1.08 exponential minus 3 multiply 0.6. This gives us 6.48 by 10 to the power of negative 4 in the j direction. Okay, so this becomes the value of the force of attraction between charge 3 and charge 1. But the question is asking us to find the resultant force, which means we need to add these two forces together. The force of charge 3 relative to charge 2 and the force of charge 3 relative to charge 1. So let's do this and see. So the resultant force is simply equal to the force of charge 3 relative to charge 1 plus the force of charge 3 relative to charge 2. F resultant is simply going to be, so F3 relative to 1 gave us this. We have 8.64 by 10 to the power of negative 4 in the I direction minus 6.48 by 10 to the power of negative 4 in the j direction, whereas the force of charge 3 relative to 2, okay, that gave us over here 2.25 by 10 to the power of negative 3 in the I direction. So we have plus 2.25 by 10 to the power of negative 3 in the I direction. So as you all know, in vectors, the I directions will add. So we simply have that resultant force, okay, becomes 8.64 by 10 to the power of negative 4 in the I direction. This is now adding weight plus 2.25 by 10 to the power of negative 3 in the I direction. So we have minus 6.48 by 10 to the power of negative 4 in the j direction. So this simply implies that the resultant force acting on that vector or on that charge is simply going to be equal to. Now let's find 8.64 by 10 to the power of negative 4 plus 2.25 by 10 to the power of negative 3. That gives us 3.11 by 10 to the power of negative 3 in the I direction minus 6.48 by 10 to the power of negative 4 in the j direction. So this becomes the value of the resultant force acting on that given force system. All right, guys, so that's how to employ vectors in solving force of attraction using the Coulomb's law. In the next video, we are going to be considering 3-point charges on an equilateral triangle and employing the Coulomb's law in solving for the force of attraction using also vectors form. I'm sure you want to be a part of that video, so do well to hit the subscribe button and of course turn on your notification bell so you don't miss out on that video when it drops. I will see you in the next video. Thanks.